the last part of dynamics, which is chapter 17, and it's essentially similar material to what we've already covered. It deals with energy and momentum, and the only difference is now we're dealing with energy in a rigid body and momentum in a rigid body, which we didn't have before. In the past, we dealt with particles, and so we didn't have any rotation, and that was one of the big parts of the problem that was missing, and that's what makes this a little more complicated. But nonetheless, there's no real new information per se that you haven't seen before. It's just a different way of looking at things. All right. So,
Professor Niebuhr.
Yes.
There's some people in the waiting room that haven't been let in yet.
Yeah, I'll get to them.
Oh, okay.
Thank you, though. Yeah, I appreciate it. Thank you. Okay, so when we look at the past, you notice how we just finished up in chapter 16 with forces and accelerations. And so that was looking at rigid bodies, where we're looking at the mass times acceleration of the center of gravity. And then we're also looking at the sum of the moments equal to the change in the angular momentum. And now with work and energy, as I said, it's the same idea, T1 plus U1 to 2 equals T2. There's nothing new in it. The only difference is with work energy, and we'll get to impulse momentum on Friday, but with work energy, we have a new concept, which is the rotation of, or the force causing a rotation. So let's go through this quickly and I'll explain that. So this is just all this slide is telling you is that there's no internal work. The net internal work is 0. So because it's a rigid body and the rigid body doesn't deform, which isn't always the case, but because we assume it's perfectly rigid and can't do anything, then we don't have to worry about that. So it's almost a moot point in a sense. But so if we look at this next slide, and this is what I was wanting to get at, was if you recall that when we dealt with force times distance, and with force times distance, that was the way in which we, and let me, actually easiest way is just do it like this. There we go. So we know that if we have a single particle going from here to here, that if this is my initial state T1, and then I add plus force times distance, that would be my U1 to 2, right? Then I'm going to get my final state T2. And we learned that already. And so we have a simple example. Something's moving, it has a certain 1/2 mv squared. You add to it a force, and let me make this. There we go. So we start off with a certain 1/2 mv squared. We add a force times distance, and we get a final 1/2 mv squared. So with particles, we didn't have any rotation. So imagine now if you had something that was spinning. Let's just make it a simple example. Let's say it's a disk. So here we have a disk that's rotating, and it has a certain omega. Now we know that turns out the rotational energy was 1/2 mv squared for linear. So for rotational, it's going to be 1/2 I omega squared, right? And that's going to be and that's because you have the moment of inertia about the center of gravity, and then it's omega. So that gives you its kinetic energy due to rotation. Now, if we say added a force, and let's say in this case we had a some force, which would be a moment. So we'll just make it a moment, just a free moment applied to it. So if we added a free moment to it, And let's say that if the thing's already rotating clockwise and we apply a moment over a certain distance. So let's say we have a moment m, and our distance is going to be not distance as linear distance, but it's going to be rotational distance. So if we apply a moment, and we could just say 10 Newton meters, but we apply that over several revolutions, maybe 10 revolutions, then if we applied that over 10 revolutions, that would be over 20 pi, right? That would be 10 revolutions. Then we would get our final condition, which would be 1/2 I omega squared, wouldn't we? And that's really what that's saying, is that we've added, and up here we've had force times distance when we're dealing with linear, but now, and we still have this in a rigid body. So this object could be translating and rotating, right? It could be going this way, right? Say the ball, it's like, think of it as a ball that's rolling. So you have, in that case, if you're going to describe this ball rolling, you're going to have 1/2 mv squared for the translation of the center of gravity. And you're going to have the plus 1/2 I omega squared, and that's for the rotation. So you have both of these, whereas in particles, you didn't have that. You only have this. So that's the big difference. Does that make sense, everybody? Hopefully that's the case. If not, then, speak up. All right. Okay. So then that's what this equation was down here. It's u1 to 2 equals m d theta. And so whether that moment is adding or taking away rotational energy, that'll determine the sign of it. And then this is essentially a summary of what I just said, but if you have both translation and rotation, you have 1/2 mv squared plus 1/2 I omega squared. And you can reduce this 1/2 r squared delta m. This, if you think about it, if you take this and simplify it and you pull out velocity, because we know that velocity is r omega, right? So if you take out that r and put it here, that becomes r squared times m. And so as a result, you end up with this being the moment of inertia. So that's essentially what the derivation is. It's the motion of the center of gravity coupled with the moment due to rotation. And that's exactly what it says. Kinetic energy associated with the motion of the mass, and kinetic energy associated with the rotation of the body about its center of gravity. And that's really all the theory there is for this section in terms of energy. Everything else is stuff that you've already done or seen. It's just adding one more piece. All right. Okay, so let's look at an example. Here we have a object sliding down, rolling down a hill, and we want to know which one's going to go farther. All right. So let me go ahead and draw that. It'd probably be easier. So we have like this, and so we start up here, and so we have, and it comes down, and then we want to know how far it goes. So we have a sphere, and it's I equals 2/5 mr squared. We have a hoop, which is I equals mr squared, and we have a cylinder, and that is I is equal to 1/2 mr squared. All right. So remember that when we talk about F equals ma, then this is really the resistance to acceleration, isn't it? If we talk about if we talk about alpha equal, if we talk about, I'm blanking, I omega, right? Talking about rotational, then this becomes my analogy to that, right? And so if I think about moments equal I alpha, then I is my analog to mass when we're talking about moving an object. So if that's the case, which one has the least moment of inertia, mass moment of inertia? That's going to be the sphere. So in a sense, the sphere is going to have the least resistance to rotation as it goes down here. And so the sphere is going to go the farthest. Okay. So that's the idea behind that problem. Okay. Let's go back to this. And then this is an interesting one. Here we have a solid steel sphere of radius r and mass m, and it's released from rest and rolls without slipping. So it goes down an incline. And so it wants to know what is its speed after rolling a distance d. And because in this case, the difference with this compared to the one previously is because we have the same moment of inertia, I equation, because they're both the same, then the velocity isn't going to change. And so this one you could look at simply as a oh, wait, I'm sorry. Did I not go to, I didn't share the screen again. I'm sorry, I'm talking here. I'm looking at it, but you guys aren't seeing it. I apologize for that. I'll blame it on the COVID. There we go. That's what I was trying to show you. Okay. So in this case, we have this. So I'll show it to you. And then this is what this is saying is if you have something like this where you have a object going downhill, if I take a sphere and I want to know what its velocity is down at here, then it doesn't matter if my r equals, if I have one with r or one with 2r, they're both going to have the same velocity at the end because they both have the same I. So I is still going to be equal to 2/5 mr squared. So the physical size of the sphere isn't going to matter. So if I had a sphere that was like this or a sphere that was like this, it's going to be the same density, the same proportions. And so it's going to end up down here. I mean, it's the same analogy to as if you were to drop, a little object in a big object and you didn't have any resistance due to wind. We know that those would both hit the ground at the same time. That's all it is. Okay. So on the final, there will be 6 out of the questions. There's usually between 5 and 6 calculations on the final. There'll be one question that'll be what we call a conceptual question, and it'll be broken into several conceptuals. So if you think of having 5 problems on the final, each one is like a calculation, like a midterm question. One of them will consist of a breakdown of 6 or more short answer conceptual questions. So I would say is that try to, as we're going through all the theory and discussions of why things happen, do your best to understand not just what numbers plug in where, but also what is actually happening physically with these. All right. Okay, so going back to this, let's go ahead and do an example. Now I did post this example on Canvas, so you should have been able to download it. But this is a good example of energy. And so in this case, what we have is a cylinder rod. And I'm going to redo, didn't have time since the last lecture to redraw my whole diagram, so I'm going to cheat and use part of it. But so let's look at the problem. So you have a spring that's stretched out, and it's from B to C, and you have this bar AC that's 2 meters. Now you're told that theta is 30 degrees, so you can see where it's sitting, and you're told that the unstretched length of the spring is 2 meters. So if you release that and it's at omega equals 0, then you can see that it's going to want to rotate clockwise, and it's going to increase in speed. And we want to know what is the speed at the moment that it crosses the point where the spring is unstretched. So essentially where the spring is 2 meters. Now, we can calculate how long the initial spring length is. And if we know the initial spring length and we know its resting is 2, then we know how much potential energy we have, don't we? So looking at this diagram, what would be the easiest way to calculate the spring's length? Any ideas? So what kind of triangle do you have there?
30, 60, 90.
Well, you have that as part of it. That's true. But you notice that what's the complement to 30 or the supplement to 30? What's
150.
the 150? So do you see that you have 2 meters from B to A and 2 meters from A to C? And so you could use which law to figure out BC? Use the law of cosines, right? So if you think about it, let's do this. Here's my drawing, okay? So bear with me, there's a few sketches on it. So here's our initial drawing here. And we have 2, 2, 30 degrees, 150. So we know that, and that's the included angle. So we know that we can write this as BC equals 2 squared plus 2 squared minus 4 times 2 times 2 times cosine 150. All right, that's just the law of cosines. So we can figure out how far that is. And it turns out that when we do that, we get a length of equal to 3.864. So that's how far BC is right now. So if I know that it rested as 2 meters, then I know that my initial length X is 1.864. Follow me so far? So we have that. All right. Now remember that we want to find omega as it sweeps around and the spring is exactly 2 meters long. So if we think about that from a drawing standpoint, that's going to look like this, isn't it? You have, here's my initial position here. It spins around to here. When that's 2 meters, this is 2 already because that's how long it is. That means I have a equilateral triangle. So my equilateral triangle then means that this angle here now is 60 degrees. This angle is still 30 degrees because that's where I started from. Now, the reason I've drawn this is because I need, there's several things to this problem that I don't have. And I want to, if I think about it in terms of its, the overall problem, we have, so if we step back and draw the generic equation for it, it's going to be what? It's going to be T1 plus U1 to 2 equals T2. All right. Or I can also write this as T1. Now T1 is 0, right? It's not, it starts at no omega, so it's 0. And then plus, and then what do I have? I have U, what I call U1 to 2, and I call that my elastic, right? And then I have plus my U, and so you can, I mean, I guess another way we could encompass all this as our V's, right? Because, and that's why I don't want to confuse you guys, but remember that this just encompasses all the changes. So we have, within that, we have the MGH, and we have plus the 1/2 kx squared, right? Because this is changing height and there's a spring component to it. And then that's going to equal to my T2 over here, which is my final. Okay. Now, so let's go ahead and So what do we have in this case? If we look at, so from a calculations, we go to here, and you notice how if I draw this U1 here, its initial position height-wise is going to be here. That's just going to be 1 meter because it's halfway over, and then 30 degrees because I want to know where its center of gravity is. The center of gravity is in the middle. So I know that 1 is just going to be 0.5 meters. Y1, I'm sorry, is 0.5. I know that Y2 then is going to be at 0.866 because that's going to be then Y2 over here. And if that's 1 meter there, then that's the opposite side of a 60-degree triangle. So really the height change from here to here, this distance there is just this, the 0.366, okay? Now, the other thing is we need to put in the parallel axis theorem, all right? We know that it's a slender rod, so it's 1/12 ml squared, but we're rotating about A, not about the center. So anytime you're not rotating about the center, you have to include this plus md squared term. So if we do that, we have 1/12 times 12 times 2 squared, that's the length, and then plus the md squared, 12 times 1. So we get a total of 16. So now we have, I think, what we need in terms of our values. So let's go ahead and write out what we're going to finish up with. So now if you don't like the U1 to 2, you can also write it like this. And there's no difference to it. It's just, and this may seem, so T1 plus V1G plus V1E equals T2 plus V1G plus V1E. And so that's kind of your generic overall, because the only thing we have is we know initial velocity is 0, right? Final velocity is going to be 1/2 16 times omega squared, right? That's going to be my final T2, and that goes here. So it's going to be 1/2 16 omega squared. And then my V1G, there's not, well, for elastic, there'll be none, right? And so the only thing that's on this side is I'm going to have to subtract off this change in height. And so that's going to be my minus 12 kilograms times the height, 9.81. So my mass times gravity times my height, which was 0.366 meters. All right. And then on the other side, I just have 1/2 40 newtons per meter, and then times 1.864 squared. All right, so let's look at what I did. So I have the spring, right? So we know that, let's think of what's going to make my, I'm starting at 0. So I start at 0, and then I have my plus my spring. So spring causes it to go faster. So that's on the left side. And then I also have a drop or a change in height, right? And that's positive. So I went from here to here. And so even though I put it negative over there, because that's how the equation was set up, from a conceptual point, or maybe it makes more sense, is I'm going to put it over here. So plus my MGH, because it's negative, so it becomes positive over here. So really, another way to write it, if it makes more sense to you, is you have 1/2 40 times 1.864 squared plus 12 times 9.8 times its change, 0.366, because we just want the net change of height. That is all going to contribute, these two things, to making this move. So that all is going to then equal my 1/2 16 kilogram meter squared times my omega final squared, or omega, whatever you want to call it. So hopefully that, in summary, because I know that some of you have expressed a confusion in terms of how do you know which side what goes on. And so again, there's no absolute correct way. I think it's just if you try to make it as simple as you can understand it. And so if it works better drawing it this way and subtracting off on the side, or if it's easier for you to understand as all of this goes into making that rod move, therefore it's all on the left. And then all I have over here, when I reach that point where the spring is relaxed, there's no more gravitational potential energy, there's no more elastic energy, so there's nothing. So all I have is that final omega. So if I solve for that, I get omega equals 3.75 rads per second. Okay. And it's going clockwise. It can't go anywhere else. Any questions on that? Does that make sense?
What number do you have written there for I? I can't really read that.
I is 16.
That's 6. Okay, thank you.
Okay. So let's look at the next one, because that one, and then we won't get to the last one. We'll do that one on Friday, but the last one encompasses rotation and translation. But let's do another example. It's a little more straightforward. Now this one has to do with the idea of the moment times a force that I discussed at the beginning. So here we have a here we have a 4 kilogram cylinder, radius of 0.15 meters. We're giving it an initial angular velocity, omega naught. And so we know with the omega naught that it is going to that's all the initial energy in the system you have is that 50 rads per second. Now suddenly you bring it into contact with B. And so now you're going to, as you can imagine, when it hits B, the first thing it's going to do is it's going to slide. There's going to be friction between the two surfaces. And then as the sliding continues, there will be an equilibrium reached, and then both will move at the same velocity. So we know the final angular velocity has to be the same because we know that that's when slipping ceases. And so we want to find that, the final velocity, and we want to find the coefficient of kinetic friction. Now, the other thing is we're told is that A executes 3 revolutions before it attains a constant velocity, whereas B only executes 1 revolution, okay? So that's important because the number of revolutions times whatever force is being applied is going to give us that moment times theta energy that we need in our equation. So here I've summarized it, and here we have 4 kilograms. I don't know why it should be in better focus. Help. Sorry, just trying to see if I can make it look better, but it's still kind of. That's still not very focused. That's worse than. All right, well, we can read it. It's not ideal, but so here we have our here's our 2 objects, A and B. We know there's friction between the 2. B is at rest. A is moving 4 kilograms. This is really annoying. And so the 0.150 is our radius. We know our initial is 50 rads per second. We want to know these 2 values, mu k and omega final. All right. So we know that A spins and slips for 3 rotations and B spins and slips for 1 rotation before they reach their final omega. All right, so this is a free body diagram of it. And so what we have is the top omega, that's the weight of the cylinder, and then AX pushing to the left, because as this thing rotates, it's going to want to push to the right. So it just has a single rotation or a single pin because it's free to slide up and down. And then it has its friction force and its normal force. And then on the lower cylinder, cylinder B, it has these reactions here also, plus the weight, and it also has a friction force and normal force. Now, we're not really going to use the stuff in the center. It's good to identify in your FBD, because if you ignore it, then you have to make sure that you account for it in your equations. Now, we're going to take the moment about the center point, and so a lot of this is going to disappear, which is nice. So one thing is we need to know is what is the I cylinder. And so I cylinder, the moment of inertia is going to be 1/2 mr squared, and that's going to equal 1/2 4 kilograms times the radius. So we get 0.045. Okay, so we have some of the basic values for it. Okay, so let's work through it. Now, we know that for cylinder A, if we sum the forces to 0 and the y to 0, this is for A, that we can calculate what the normal force is. We know the normal force is just going to equal the weight, which is 4 kilograms times 9.81, which is 39.2 newtons. So I know the normal force is that. Therefore, my friction force, since it's sliding, is going to be mu k times 39.2. All right. Now, my initial kinetic energy, so my T1 is going to equal 1/2 I omega squared, or 1/2 of 0.045, and then it's going at 50, so 50 squared, right, rods per second. And so that gives me a value of 56.25 Newton meters. Okay, so this is my energy due to the initial velocity of everything. All right, then if I look at my final kinetic energy, that's just going to be equal to I omega squared. So I can also say, we say it as T final, or T2 equals 1/2 0.045 times omega final squared. All right. And so that's could also be written as just 0.0225 omega final squared. So that's the final energy for A. So remember that for A, we also had, if we take the sum of the moments about the center point in the middle, then we know that's just going to be the friction force times the radius. Okay, now where do I get that? If I think about it, this is my object, right? If I take the moment about the center point here, then I know that my friction force times the radius, that's going to equal my moment. So if I know that friction force is going to be mu k 39.2, so I know that I have mu k 39.2, right? That's the friction force I determined earlier. God, this is so bad, this focus. I'm really sorry about that. was working better earlier. Let's see if I, no, the light won't change anything. All right, so I'll just have to draw bigger. Friction force times radius. All right, so mu k is 39.2. All right, and then if I multiply that by the radius of 0.15, then what I end up with is 5.88 mu k in Newton meters. All right. Now, remember that we have our T1 plus U1 to 2 equals T2. So we have our initial value, and that was 56.25. Then we have this mu1, 2. So that's going to be essentially the moment. Remember, this is my moment here. So that's going to be 5.88 times mu k. And then it's going to be times 6 pi, right? Because it goes for 3 revolutions. And it's going to be negative. So imagine that this is my initial rotational energy. And then because of the moment of friction, then this 5.8 times mu k, which came from up here, that's going to be then multiplied. That's my moment times my theta. So m times theta, and theta being 3 revolutions. So that's going to take away from my final T2, which is just going to be equal to 0.0225 omega final squared. All right. So I have this first equation here, I'll call equation 1, and I have 2 unknowns. I have mu k and omega final. So in order to solve, I'm going to have to go to disk B. So disk B will be done similar in this, because what I'll have to do in that case is I'll just have to set up the same thing. So for disk B, we have T1 in this case is 0, right? Because disk B is at rest. And then we know that it's going to be, in order to figure out what it's going to rotate, we know that it's going to have T1 plus U1 to 2. Well, it's going to have the same friction, right? It's going to have the same 5.88 mu k. The only difference is it's going to be, instead of negative, it's going to be positive, because it's going to be a force that's causing it to rotate. So 5.88 mu k, but it only took 1 rotation, so times 2 pi. Okay. So the first one took 3 rotations, and it was taking away from the energy. This one, disk B, started at 0, and then you added this friction force. And again, that's just this is just normal force times mu k times the radius. So that's just 39.2 times 0.15. That's where that comes from. And then times 1 revolution. And then that is going to equal the final, which is just the same as this, right? 0.0225 omega final squared, because A and B are moving in the same direction. So this is equation 2. All right. So you really can you have 2 equations, 2 unknowns. If you set them up, if we rewrite them, we have 0.0225 omega final squared minus 36.98 mu k equals 0. No, not 0. Yeah, that would be 0. Yeah, equals 0. And then that would be, if we rewrote this one, this is equation 2. And then if we rewrote equation 1, we'd have 0.22025 omega final squared. And that would be, in that case, plus 110.8 mu k, and that would equal 56.25. That's equation 1. So we could add or subtract, we can multiply through and then add or subtract whatever we want to do, but we'll get rid of this term. And then we can subsequently solve. And so then it's just algebra at that point because you have the 2. So when we solve, we end up with mu k equal to 0.38 and our omega final to be 25 radians per second. And they're opposite directions, obviously, between A and B, depending on the direction. So A was initially rotating, I believe it was clockwise. So B is going to be the counterclockwise. So backing up with this problem, does everything make sense so far? Because that's the important part, not just plugging in numbers, but where I got this from. So in this one, the only concept that's different is that you had this force times distance, which then became this moment times the distance. So your moment times theta, which was this here. This is just m theta. So you had an initial velocity minus an m theta equals a final velocity, an angular velocity. Now, this object didn't translate. So if it had translated, then we would have had to have dealt with that too. And that's what the next problem is about. But before we talk a little bit about that, is there any questions on anything so far?
Could you go back to the sheet right before this one real quick, please?
This one?
Yeah, I just missed something at the bottom of it. Oh, perfect. Thank you.
Anything else? Did you get what you needed?
Yeah, I'm good. Thank you.
Okay, sure. All right. So going back to this, here we have this last one. Now we'll have to do this on Friday, but I just wanted to talk a little about beforehand. Now this is a good example problem. This would be something that would be, it's not a final, it wouldn't be on the final since I'm showing to you, but this would be a good example of a problem that could be on the final. And because what it does is it shows you how you have translation and rotation. Now, if you just visualize this without doing any numbers, you think about this, you apply a force P at this 5 kilogram object, and it's going to go down 1 meter. So it's basically going to sink 1 meter. Now it's going to hit the ground. And so one of the questions, B, it says, first you want to know the velocity of the cylinder A as it strikes the ground, and you want to know the total distance that the block B moves before coming to rest. Now, if block B moves 1 meter before it stops, we know that can only go 1 meter, but that doesn't mean that block B is only going to move 1 meter. So if you think about it, this A is going to accelerate downward, but we have to account for the fact that it's being resisted by the 15 kilograms that has friction, plus it's going up an incline. And you also have to consider that once A hits the ground, B is going to continue moving because it's going to have some final velocity also, and it doesn't just stop instantly. So it's going to continue to slide up the hill until it reaches 0. And the cord will just, we'll assume the cord, it has a negligible mass, and so it will just essentially collapse on itself. So it has, the cord itself doesn't matter at that point. But so this one has both rotational I due to the pulley, and it also has translational velocity due to the motion of B. But I think if you as we go through this problem on Friday, you'll see that it's pretty straightforward in the senses that you just have to keep track of what's what. You know that A is losing mgh. And so it's as it goes down, it's losing potential energy, but essentially that's adding potential energy to the system, right? So 5 kilograms times gravity times 1 meter, that's energy that is helping that 15 kilograms slide up the hill. Now, of course, the 15 kilograms is fighting it because it's going up sine 30 degrees of times that mgh. So, and then you also have to account for the resistance of the pulley. So there's, as I said, a few things going on in here, but this will be a good example to break all those out and then keep them consistent so that you just set up one energy equation like we did in the last 2 examples. Okay, so it's a little bit to digest. So I will, that's all we'll do for today, but we will pick this up on Friday. So I'll be in my office hour from 11:10 till noon today. The new assignment is posted. It's due middle of next week. So if you have any questions, I'll see you in office hour. Otherwise, we'll have virtual class again Friday, and then we have the holiday weekend, and then I'll definitely be back on Wednesday. Okay?
Professor Neighbor,
Yes.
could you please go back to the first problem that you did, like the work for it?
I record, I mean, I can, but I also recorded this and I'm going to post it on Canvas. But what work was it you're referring to?
It was just like the first like calculations of where you got like the distance of the spring and stuff like that.
So about this. So yeah, so you have on that one, you have 2 and 150 degrees. So use law cosines for that.
Okay, awesome. Thank you.
Is that all you need?
Yeah. I just didn't get it all written down.
Oh, okay. No, that's fine. But yeah, if there's anything else that you missed, I am going to post these though, just in case. But
Okay, thank
otherwise,
you.
all right. Okay, you guys, you have a good rest of your day. And if you, I'll be in office hours in about 10 minutes. Okay. Thanks.